All right, thank you. Thank you very much for the kind invitation to speak here. Very excited to be here again. Last time I was here was before the pandemic, but it's always lovely to be back in ICTS. I apologize for the drilling. Okay, so today I'd like to discuss with you a possible new notion of quantum ergodicity for general quantum systems with general time dependence. So this is work which is going to be out in the archive hopefully soon, hopefully later this week or next week at the latest, and done in collaboration with Saul, Jaren, and so on at MIT, Harvard, and MIT. Okay, so let's start the stage or set the stage. Since I'm talking about ergodicity, the question is, oh man, sorry. Okay, so to set the stage, since I'm talking about quantum ergodicity, so the question is, what is quantum ergodicity to begin with? Now, I don't think that there's a universally accepted definition, but oftentimes we are all familiar with the use of like statistical properties of eigenstates or stationary states to define ergodicity. And this is usually phrased in terms of like, say, statistics of energy eigenstates or energy eigenvalues. So in particular, we have notions such as asking about correlations between energy eigenvalues, ask if they repel each other and if they follow predictions from random matrix theory. And this is captured by using the spectral form factor. Or we could ask if the wave functions or quantum states in the system themselves, they behave like random vectors. And we have two notions of what this means for single particle systems and many body systems. Various conjectures say that wave functions look locally like random plane waves, and the ETH, the eigenstate thermalization hypothesis, says that many body eigenstates look like random vectors locally. But what we notice about all these so-called definitions of quantum ergodicity is that they are all focused upon stationary states of the system, but not all quantum systems have stationary states. So this naturally leads to the question that I want to ask, which is, can there be a notion of quantum ergodicity in systems which are still closed, but have a general time dependence governed by some quantum Hamiltonian h of t? Is there a notion in which we can say one is more ergodic than another system? I should mention that these systems that we're considering are not just abstract theoretical questions. We can realize them in the lab because of the advances in controls and coherence times in the AMO systems. So in particular, synthetic quantum systems allow us to really engineer such dynamics, h of t, which is generally time dependent. Now, if you don't really like this very abstract question of what is quantum ergodicity in closed time-dependent systems, we can ask a more physical question. Let's suppose that my system is many body in nature, is extensive, has many degrees of freedom, but is governed by a Hamiltonian which is time-dependent. Is there a notion in which such systems, extended systems, equilibrate or thermalize? Locally, what happens to them? Do we still expect thermalization, for example, to infinite temperature? And if that is the case, then what is the mechanism behind that thermalization? Now we don't have the ETH to tell us properties of the eigenstates in local observables. So how can we understand the emergence of quantum thermalization in this setting? All right, so with that, this is the outline of my talk. I'll describe this notion, new notion of ergodicity that we're trying to propose. I'm not saying that this is the one and only definition, but this is one possible extension to what we know. I'm going to call this complete Hilbert space ergodicity. And I'll demonstrate CHSE in a family of time quasi-periodic drives, which are given by the generalized Fibonacci drives. And then I'll discuss the physical and conceptual implications of systems that have this new notion of ergodicity, CHSE. All right, so to answer the question, how can we define a notion of ergodicity for quantum systems without reference to stationary states? Let's take a step back and recall how ergodicity is defined in classical dynamical systems. So in such systems, we have a dynamical map, phi of t, and it's evolving a phase space coordinate in time. So see x of 0 gets maps to x of t. And when we say that the system is ergodic classically, usually we think of the condition where if you begin with almost any initial state, then the time average of points or functions evaluated on a trajectory in time is the same as though you're evaluating that function over the space, the ambient space that it is evolving in, the phase space. So this is usually how we think of ergodicity from the get-go. So it is quite interesting to note that quantum ergodicity doesn't really talk about such averages. So we notice that this offers us a possible route towards asking the question, can there be quantum systems which obey such a generalization of this property? So suppose let's quantize all these objects. So what I mean by that, and I put quantize in quotation marks, not really formally quantize, but just to make analogies, where we promote the phase space to the Hilbert space and points on a phase space xt to just quantum states living in the Hilbert space, and functions on the phase space to be functions on the Hilbert space. And let me then define a quantum dynamics to have complete Hilbert space ergodicity, or to be completely Hilbert space ergodic, if for any initial state and any function f on the Hilbert space, the time averages equal the space averaging. So in this case, what the space averaging is I'm going to take it to be the Haar average over all possible states over the Hilbert space. And this is a uniform measure over the Hilbert space. So one might ask, why do we do this? Well, this is the most natural definition of a spatial averaging. So let's run with it. Of course, we can generalize this and make this, add bells and whistles to this. So I'm going to call dynamics to be CHSE if this is true. Pictorially, what does this look like? So the intuitive picture of a system which exhibits CHSE is that in time, it is one in which the wave function evolves over time and eventually covers all the phase space uniformly, regardless of where you put the initial point. So in this case, I'm illustrating it for a 1-qubit system. So we can draw in a block sphere. Every point is just a point. Every wave function is a point of the block sphere. And if we consider the entire ensemble of wave functions, over time, they uniformly cover this. This is actually not a cartoon. This comes from a real simulation. So just a teaser that there are systems which are CHSE. Okay, so how can we think of CHSE in more physical terms? Because I defined it in terms of averaging over functions, and that seems like a very unwieldy concept. Well, if you think about special functions, say functions which only depend on a copy of the wave function, so that would amount to looking at the expectation value over a local observable or some observable, and then we ask, what's the average over time? And CHSE basically amounts to asking if the time average of this quantity, of this expectation value, is equal to the Haar averaging of this observable evaluated over random states. And in this case, we can always do the calculus or do the integral, and this is very standard from Weingarten calculus. We see that this basically is a condition where the average expectation value over time is equal to the infinite temperature thermalization of the local observable. Now we can go further and consider 2-point functions in time. So instead of one O of t in time, we can consider 2 different observables evaluated at the same time, and then we average over them in time. And then we can ask if this is equal to this quantity over here, where d phi is really the averaging over the Hilbert space. And we can also do the calculation and get this result. So one thing I should note is that this 2-point function is not the same 2-point function that we're usually used to. So this has 2 wave functions involved in it. This is not just 2-point functions separated by space and time evaluated within one copy of the wave function. And so this probes things like fluctuations. So CHSE can be rephrased in this formulation where we say that every k-point function matches the time averaging of every k-point function is equal to space averaging of every k-point function. And a very compact way of packaging all this information is to construct these density operators on the replicated Hilbert space. So what they are is that you take each wave function in time, raise it to the kth power, and by raise, I mean you take the tensor product of it, and then you take the average of this. And this really gives rise to, this really captures all the possible temporal moments of this ensemble of wave functions over time. We can do the same for wave functions defined over the Hilbert space. And then basically, CHSE is a condition where this temporal moment operator matches the Hilbert space moment operator for every k, and k here is the power of the function. Okay, so quantitatively, we can capture this by introducing a norm. Because these objects are density matrices, we can use the very standard trace norm, which is used in quantum information theory. And then this is just the, indeed, the trace distance between the 2 of them, the 2 ensembles. And CHSE is a condition that in the limit as time goes to infinity, so this big T here is not temperature, it's time, that the distances goes to 0 for all k and almost all initial states. In other words, if I may invoke some jargon from quantum information theory, we're asking if the ensemble of wave functions in time forms a so-called quantum state design. Okay, so now we can ask, where can we find systems, or which systems have CHSE? And we have our first result, which is that we have a no-go theorem for systems which are time independent. So here, I think it's like, so, okay, so this theorem tells us that there's a lower bound on the trace distance for any initial state. So let quantum dynamics in a d-dimensional space be generated by a time independent Hamiltonian. And this has eigenstates h of n is equals to en n. And then what we could show rigorously is that if you compute the trace distance for any moment which is greater than the first moment, so second, third, fourth moment, then there's always going to be a finite distance away from zero, which is a function of the Hilbert space dimension. And Hilbert and CHSE cannot be achieved in these systems. Now, this is perhaps not surprising at all, very intuitively clear why. It's because in dynamics of a time-independent Hamiltonian, the population of eigenstates is conserved, which means to say that a state cannot uniformly cover the Hilbert space in time. You have perhaps only the ability to cover it uniformly in time at the level of the first moment, where you choose a particular initial state carefully. But aside from that, any other choice of initial state will never ever cover the Hilbert space over time. And by similar token, Fouquet systems or time periodically driven systems exhibit a similar no-go theorem, not quite phrased in the same way, but I mean, sorry, not quite the same expression, but phrased in the same way. And that's because Fouquet systems themselves have also quasi-energy states, which precludes exploration of the Hilbert space over time. So this means to say that our definition of complete Hilbert space ergodicity is really more suited for systems which have time dependence, which are not time independent or time periodic. They are more general in nature. So what is a system that does exhibit CHSE? Well, if you think about it, maybe one system which is very natural that comes to mind is a random drive. So let's say that we pick two unitaries, A0 and A1, acting on a d-dimensional system, and we just pick them and fix them afterwards. We don't modify them anymore. And then we're going to generate dynamics in such a way. We're going to let time be discrete. T is 1 to 3 to 10 to 100. And then at every time step, we're going to apply the unitaries A0 or A1 with equal probability. So for example, one instance of such an evolution corresponds to the application of A0, A1 along this time sequence. And one could ask then, suppose I look at the wave function at time 0, which is the initial state, the next wave function at time 1, the next wave function at time 2, and I collect all the wave functions and probe their statistics. How well do they cover the Hilbert space? Yes. Right? Caveats of I think it's quantum because that comes about from the linearity of the well, the fact that you can decompose it into eigenstates. The fact, I guess, that is linear, yes. Yeah. So if you have a dynamical map, which is that's not entirely true actually, but yeah. It's a conserved charge, yeah. Basically, I guess it's a conserved, Hamiltonian itself is conserved dynamics. So that's why. Yeah. All right. Okay, yeah. Great. So now I'm going to look at this sequence of wave functions in time and ask if they cover the Hilbert space. And one can show, not surprisingly, that almost surely for any choice of A0 and A1, and for almost all instances, any instances of this long evolution, this dynamics exhibits CHSE. Of course, there are some failure modes where if you pick A0 and A1 to be the identity, then of course this doesn't cover the Hilbert space. But basically, this theorem tells us that very surely, almost surely, you will always achieve complete Hilbert space ergodicity. But this is not surprising, as I've mentioned multiple times, and this is because the randomness of the dynamics is what underlies the uniform coverage of Hilbert space. More precisely, this sequence of zeros and ones, they have what is known as high symbolic complexity. So symbolic complexity is a function that depends on n, N is basically the length of a contiguous subword. And basically it's computing how many subwords appear, how many distinct subwords appear of length N. So in the case for a binary random drive, one can easily show that almost surely this symbolic complexity is exponentially large to the power of N, which implies that, which basically means that all possible zeros and ones appear. And if all possible zeros and ones appear, it means that then the unitary obtained by concatenating all the zeros and ones for any string is really going to reach every point in the Hilbert space. And so the more physical question I want to ask is, are there simple low complexity drives which still exhibit CHSE, which doesn't require this high symbolic randomness? Okay, so I am going to introduce this new drive. Is defined on what is known as the Fibonacci word. I think most of you are familiar with it, but let me run you through it. Consider two characters, 0, 1 of an alphabet. So it's just binary alphabet. And let's take W0 to be the word 0, W1 to be the word 0, 1. And then I'm going to generate the words, future words, further words, by concatenating the two of them. So W2 is equals to the concatenation of W1 and W0, and that gives me W2. W3 is the concatenation of W2 and W1. That gives me a new word, and so on and so forth. So we see that the rule is that Wj is equal to Wj minus 1, Wj minus 2. And from there, before that, so the reason why it's called the Fibonacci word is because if you count the number of terms that appear at every level here, this is equal to the Fibonacci number, as you can visually identify, because this is basically Fn is equal to Fn minus 1 plus Fn minus 2, which is the definition for Fibonacci number. And using this word, I'm going to define this Fibonacci drive, which is basically substituting 0 for a unitary A0 and substituting 1 for unitary A1. And then I'm going to apply the sequence in time. So this set of unitaries is going to be having this recurrence relation. The set of wave functions I'm going to look at over time is not defined at every Fibonacci time, but rather at every discrete time. So this really defines an aperiodic quantum drive. It never repeats itself over time. And one can check that, right. So one can check that indeed it is neither time independent nor time periodic. I refer you to this work where there's been some studies done on such a drive. Okay, before moving on, let me introduce a bigger family of similar drives. So instead of just taking the previous unitary and concatenating it with, instead of defining U of Fj to be the previous unitary and the previous level, I can apply m times. So I'm going to introduce just an index m. It's just a way of defining a whole family of drives. And so in the case when m is 1, this is what we saw before, the Fibonacci word or Fibonacci drive. In the case when m is 2, so I repeat this twice before I repeat the process. This is what is known as a Pell word, not as commonly known, but still common enough to have a name. And just as an interesting aside, the number of terms A0, the number of terms A1 for a long sequence, as you all know, this is the golden ratio. But the number of terms of A0 to A1, this is known as the silver ratio. And for every m, this is known as a metallic ratio. So I've no idea why or what the etymology of this word is, why it's metallic, but let's just take it as it is. Okay, all these sets of drives, they're all deterministic, as can be shown, as can be seen. Furthermore, they're all time quasi-periodic. And this is because you can think of them as arising from a Hamiltonian, which is driven by two incommensurate frequencies. It's hard to write it down. Maybe it's not hard to write it down, but I think it's easiest to just visualize this. So imagine that we have a torus. We draw this region to be blue, this region to be orange, and the length of this region is really set by the ratio, the metallic ratio. And then we consider a winding around the torus at some irrational angle around the cycles. And then we see that every time we cross this circle, we're going to pick up this orange and blue. And trust me that this gives rise to the sequence over time. And if we modify the length of orange to blue, this gives us a Pell sequence as well. So clearly this is a time quasi-periodic drive because this is factorizable over the torus. It has only two frequencies and which are incommensurate. Furthermore, all these words, all the 0, 1s that we are defining the drive from, they all have simple and in fact minimal symbolic complexity, which is n plus 1. So if you look at any subsequence of length n, you only ever find n plus 1 distinct subwords. And in fact, this is the minimum possible for any sequence which is aperiodic. Anything which is below that is going to be necessarily eventually repeating over time, which means that it's going to be essentially Fouquet-like in nature. Okay, our main result is simple. For almost any, for any order m, almost surely the Fibonacci drives exhibit CHSE. Okay, that's just the statement of our theorem. We can prove this rigorously. Let me show you some numerics to support this claim. So here I'm doing numerics for m equals to 1. So I'm just considering the basic Fibonacci word for a single qubit. I'm applying A0 and A1 to be 2 rotations, one rotation about the x-axis, one rotation about the z-axis for different angles. So this is a busy slide, but let me walk you through it. Let's just focus on this orange one, which is one set of angles that I'm rotating about. And then you have this solid one and this slightly faded line. They represent different initial states. So you see that they go down in time. And then for different values of rotations, you get different curves. And this dashed line is a bound that we got from the time-independent case. So clearly we see that some of them are going down below this line, and therefore, basically, they are more ergodic than what time-independent systems can give you. We can zoom out. We can go to much longer times and see the behavior. And some numerics that was done up to 10 to the power of 200 time steps show that eventually all of them go well below the bound with a distinctive power law with not much difference between the initial states. Okay, so they only depend on the rotation angles that we are rotating by. Okay, so I think this is strong evidence that this system has CHSE. Okay, next, let's consider a many body system. So 2 unitaries A0 and A1, given by rotations, given by an Ising model in the x direction, and an Ising model in the z direction. And then I'm going to apply them according to the Fibonacci drive. And this is what we see for different moments, 3, 2, and different sizes, 4 and 5. You see this goes also below the bound. So eventually you can imagine that this will go to 0. Okay, so the next few slides are just going to be more technical. So if you don't really follow all of them, that's okay. But I just wanted to give you a flavor of how we managed to prove such a result of CHSE in this class of models. So what we want, I'm sorry? Yeah, so yeah, that's a good observation. So indeed, we don't really have any understanding for why this rate is 1 over square root t. In this case, it seems to be universal for many body system. And this, I think, is also the rate for a random drive as well. So essentially, a Fibonacci drive is doing as well as a random drive in randomizing your wave functions. Why this happens, we don't know, because the proof of which I'm going to describe only tells us what the limit is. It doesn't actually tell us what the rate of convergence towards the limit is. All right, so very quickly, not very quickly, but 3 slides of technical slides. And if you don't follow, that's okay. Okay, so what I'd like to do is understand this temporal ensemble, rho of k of t. Now it turns out that I can pass it through a quantum channel, n of t. And n of t is really just the time averaging over all possible u of t's. U of t's is the time evolution operator. And basically, we can focus our attention not on the temporal ensemble, but on the channel that randomizes the state, that randomizes the state over time. So our goal is to show that the infinite time randomization or infinite time averaging is right invariant under any unitary channel. And the reason why this is sufficient is because there is only a unique averaging channel which is right invariant under any unitary channel. So sorry, I'll say that one more time. There's only one quantum channel which is right invariant under any unitary channel, and that is the high averaging channel. So once we can show that, then we are done, because then basically your state will be high average over space as well. Okay. Next, this comes about from the recursive relation of the Fibonacci drive. One can easily show with a small bit of work that there's a recursive relation, not only for the unitaries defining the Fibonacci drives, but also the time averaging channels. So the one time averaging channel at one time is related to another time with some ratios up to a unitary channel, which is U at Fn minus 2. So what we would like to do if we see this equation is to take a limit as n goes to infinity, because then we could replace everything by n infinity, and n infinity. But unfortunately, this unitary channel does not have a limit, naively speaking, because my unitaries are always evolving in time. But it turns out that because of the quasi-periodic nature of the drive, together with the Poincare recurrence theorem, what we can do is instead of taking it along all integers, 1, 2, 3, 4, 5, the limit of it, we can take it along certain subsequences of time. So we can choose a particular subsequence of times to evaluate what this limit is as time goes to infinity. And we can show that the two limits are in fact the two beginning unitaries. This involves some complicated, not complicated, but some clever construction of this map to invoke the Poincare recurrence theorem. But basically, this shows you that there are two limits that we can define, A0 and A1, at least two limits. And in a nutshell, what that means is that if the time averaging channel, after you do all this, like this massaging of equations, it obeys this right invariance, where n infinity of k is right invariant under unitary averaging under A0 and A1. But not only do we have this, we can form an arbitrarily long product of A0s and A1s, and then there'll be right invariant under any unitary average under this long concatenation of all possible A0s and A1s. And the last step is then very simple. We invoke a very well-known theorem or concept from quantum information theory, which tells us that for any choice of A0s and A1s, if you pick them randomly over the unitary group, they are universal gates. You can cover the entire unitary space eventually. So this implies that then the infinite time averaging channel is right invariant under any unitary channel, which then implies that it is the hard averaging channel. So that is the main technical proof of this theorem. Okay, so now let's move on to some implications of CHSE in terms of both physical and conceptual implications. I think that's interesting. So one is that we have a statement, which is that the time evolved wave function looks like a random vector in Hilbert space. It is basically indistinguishable from the point of view of statistics over time from a random vector. And we know that for a many body system, a random vector is going to be nearly maximally entangled. Therefore, if you look at a small subsystem, this implies that at late times, quantum systems which exhibit CHSE thermalizes locally to the maximally mixed thermal state. Not only do we have that, this also gives us very strong conditions on what the size of the fluctuations are. In particular, the size of fluctuations are going to be 1 over square root d. And not only that, we have information about how the higher moments also scale with system size. Okay, so this is a very stringent form of thermalization. Moreover, we have the emergence of deep thermalization. So this is a relatively new concept that I've been working on together with a bunch of other people in the audience. So let me very quickly, in one slide, explain the main picture of it. So here is very similar to quantum thermalization. Looking at a local subsystem, we divide the system into two parts, B and A, and we treat B as a system's bath, as a bath for A. But instead of tracing out the degrees of freedom of B, let's assume that we're able to understand what its state is classically. That is to say, let's assume that we can measure it and we understand what its state gets updated to. Now, this then induces a pure state on A. So this becomes a conditional state that depends on the classical state of the bath. And then we can consider the entire collection of all possible conditional states on system A. And deep thermalization is really the emergence of a uniform distribution of conditional local wave functions. So as you measure more and more spins, then this is going to fill up the Bloch sphere or the Hilbert space uniformly over time. This is a new kind of universality that we have kind of uncovered. And so basically CHSE systems implies deep thermalization. One last point, which is the on perhaps a bit more mathematical implications, is the irreducibility of Fibonacci drives. So to explain what this is, Okay, so recall time periodic systems and Fouquet's theorem. So a time periodic system is one in which a Hamiltonian repeats itself over time. And as we have heard previously in the talk, there's a notion of Fouquet's theorem where we can decompose any wave function in terms of quasi-energies and quasi-energy states, which are themselves time periodic. If I now promote this, so we call this dynamics reducible because you can reduce it in such factorizable form. Now, if you consider a quasi-periodic systems, the obvious generalization of a Fouquet system, that is, if you promote this Fourier mode n to become a vector of Fourier modes and omega, the frequencies, be a vector of frequencies with some suitable irrationality conditions, does there exist a generalized Fouquet decomposition, which is to say that if I drive my quantum system with a time quasi-periodic Hamiltonian, is my wave function going to be decomposable into, once again, quasi-energy states and quasi-energy states and quasi-energies, where the quasi-energy states are themselves time quasi-periodic? Turns out that the answer is sometimes yes and sometimes no. Sometimes it behaves like the Fouquet systems and sometimes no. So there is no Fouquet theorem here, but interestingly enough, there are cases in which you can find a generalized decomposition and some cases where there are obstructions to it, either from topology or from energetic reasons. And evidently, our results show that the Fibonacci drives, which are time quasi-periodic, which display CHSE, cannot possibly have quasi-energy states and hence are not reducible. Because as I mentioned before, that would preclude exploration of Hilbert space. Okay, so with that, that's the end of my talk. The summary is this: I've introduced a new notion of quantum ergodicity, which is more suitable for quantum systems which have general time dependence. And I've demonstrated how it occurs in systems, in a family of systems with various physical and mathematical implications. Some outlooks include, so I've kind of given examples of when it occurs, but maybe we need to formulate more properly when, what the general conditions for CHSE to occur are. And secondly, is it possible to account for some symmetries in this framework? And if so, how does it relate to our usual notions of quantum ergodicity in terms of the statistics of energy eigenstates and energy eigenvalues? Thirdly, so there's been a lot of interest in the quantum information community in studying circuit complexity growth, which is basically asking if I apply a bunch of unitaries, well, if my state is evolving in time, how can I decompose the evolution into small unitaries, small local unitaries? What's the minimal depth that I need to apply? And that's the notion of circuit complexity. Now in CHSE, because these systems are random, eventually going to be random vectors in time, maybe this constitute arenas for rigorous studies of circuit complexity growth. And fourthly, because CHSE basically gives rise to averaging over a unitary group, can this be leveraged as a practical tool for quasi-Monte Carlo sampling over the unitary group? And with that, I thank you for your time, but I would also like to very quickly flash an advertisement. I'm hiring postdocs and graduate students at the National University of Singapore and Center for Quantum Technologies. This is a nice picture of Singapore here, not too far from India, 4 hours. So if anyone's interested in quantum many body dynamics, information science, AMO systems, please feel free to contact me. And with that, I thank you for your time.
Questions?
So I think you already commented briefly on this, the relationship with chaos, like this aperiodic drive. Can you study yet and whether it has signatures of other chaos stuff?
Sorry, can I study what, sir?
As in, you have the aperiodic drive.
Yes.
What's the relationship between these kind of time evolutions and time evolutions that we consider to be chaotic?
Right. So I think then that depends on how you define chaos, I guess. So for example, if you ask, Fouquet systems are chaotic if they have a spectral form factor which exhibits a ramp. But then the question is here, can we even define spectral form factors? What does it mean to have correlations between eigenvalues which don't even exist? So
temporal random versions of
So you think there will be temporal versions? Okay. Yeah, let's brainstorm about that.
The other thing is, I mean, we mentioned about these Hamiltonian quantities, but we can also conserve. temporally random evolution with conserved quantity.
Yes.
And have you guys tried? Or?
No, so no, we have not tried. So that'll be inclusive, including symmetries into the game. All right.
See. Oh, now we're there. Yeah, nice. So I want to come back to this power law decay as a function of time, like Sarang's question, basically. I mean, I'm gonna try to pitch what this answer is.
So you're gonna prove y is 1/2?
Yeah.
Okay. Very
I think it cannot be faster than 1/2 for the same reason you're writing here, namely that it should be a study of the circuit complexity. So since this thing you produce has to produce the all Haar random unitaries, well, you just have to count how many there are. And so the number of them is the volume of this entire space. The space is all unitaries that go between, there are d by d matrices. So the space is the volume of this sphere in this d squared dimensional space.
Right.
So and at the end of the day, the entropy or the number of bits that you need to specify is d squared. So you need a sequence in time that's at least d squared long to do this. So that basically means that this cannot decay fast. If you want then to get an error which is below your bound of a conserved thing, you need to go below 1/d because that's what you would naively get.
Right.
So then it means that it needs
I
to go like 1/square. Yeah.
Right. I think your argument needs to also incorporate the moment as well, because
Exactly. That's
because we have numerics as well that shows you, for example, the single qubit. This is much faster than 1/2.
Yeah. So for the first moment,
particular moment too.
Yeah. Exactly.
So I think this must be some.
But I think you've basically give the last question is the answer to your power, I guess.
Okay, thank you. Great.
Thank you for the nice talk. So, you can think of the Fibonacci sequence as a projection of a periodic sequence in higher dimension, right? So, I'm wondering if it's possible to think of your time, Fibonacci time evolution as a kind of a shadow of, some periodic time evolution in higher dimension in which you have, many different time directions. Maybe it's a crazy question, but.
No, it's not a crazy question, but I think that that's the essence of what a time quasi-periodic system is, right? Because you can always define a system on multiple times as a theories construct. If you have two frequencies, you can define it on 2 different times. And then our real drive is really the one in which I'm projecting along t equals t prime. And I just don't know how much more insight that would give me, basically. But I think what you say is completely correct. We can always think of it as a projection in one time direction.
Can I ask another question? So, so actually, what is the precise condition under which the Poincare recurrence theorem works?
Yeah, the precise condition is when you have a measure preserving map. Okay, if you are guaranteed a measure preserving map, then for almost all initial conditions, there will be a subsequence of iterations of the map such that you will come back arbitrarily close to that initial condition. There'll be some measure 0 points which fail, but it's part of the theorem. With measure 1, all points, with almost surely all points.
Is it really easy to verify that the Fibonacci protocol satisfies that condition?
So the way that we proved it, I mentioned in the sketch, was that we invoked it here. And we used the Poincare recurrence theorem on a cleverly chosen dynamical map that relates 2 time evolution operators at some time to another time. So it's like a dynamical map on the space of SUD cross SUD. It's a bit too complicated to write down right now, but essentially, it's once you see the form of it, it's easy enough to understand it.
Thank you.
More questions? So I have a short question.
Yes.
So What about two-time correlators?
Two-time correlators.
Yeah. Okay, can you write?
Right.
How does it?
So two-time correlators in yeah, but two-time correlators in the same wave function, right?
No, that's I don't know, but I was asking related to your definition of ergodicity.
Right.
And write down what does it mean for two-time correlators?
Yeah. Yeah. So we don't have a two-time correlator in the sense that we are probing correlations at the same time, but just average over all times.
Yeah.
So if you want to promote that to two-time correlators, then
I'm asking
yeah,
if it's possible.
no, it is possible, but you would have to then to promote the objects that you're studying to not just the wave functions in time. I guess you would define it on something more complex, like two-time wave. Like, yeah, it's a bit hard to say what it is. It's possible. I think it's possible, but it's just I don't have a clear picture of what it should be right now.
Okay, so thank you very much.
Thank you.